Hello, everybody. My name is Kevin Kocek. I'm the founder and CEO of Chemical Q Device, here for discussion 115. This is Thursday, December 28th, 2023, for quantum algorithms and parallel architectures. This is going to be new results and also the progression of it all. So the biggest thing with this is you can run in Keras or Torch, and I've kind of nailed down some of the issues with the Keras. It's with the sequential, it looks like. So sequential you would usually use for like a single quantum circuit, and then the Keras equivalent of module, meaning for the neural networks, seems to be okay as long as you run a certain version of TensorFlow. Now, with these, there's an issue with PyTorch, Keras, and PennyLane, or Qiskit with GPUs at this point. I don't know if it's just a switch they need to flip, but basically all of these were run on a high RAM CPU, which actually gets me 51 gigs. And actually, I couldn't have gotten that with top of the line A100 40 gigs. So it's a good thing. And so basically, there was some verification between the results on a single quantum circuit on torch.nn.sequential versus torch.nn.module. Module is the one that you use neural networks for, so in parallel or whatever you want to design on your own. And then there was also batch size, learning rate, dataset noise. And a lot of these are still valid as kind of like an entry point, but the majority of the more intense experiments were done with Torch. PennyLane also recommends running Torch with these. So you see this is basically accuracy, RAM, and time. There's benefits in doing parallel circuits and parallel algorithms, these quantum circuits, as opposed to doing a big quantum circuit, with many qubits. And I'll show you the results with that. And there's also probably the pinnacle or the biggest study of this is basically taking everything, learning rate, batch size, algorithm type for quantum circuits versus one other one, and learning rate. So there's 4 plus the layers, and the layers actually had the biggest impact, and it wasn't on intention. I picked the usable ranges for each of those, found out what they were, and then whatever had the lowest loss, and and I'll show you with the layers here. So also embeddings versus other types of algorithms were looked at. And if the embedding isn't correct, then when you add these variational circuits, meaning the trainable part or what truly makes it a quantum machine learning algorithm, if the embedding is not good, then the trainable part will not be good. And the majority of the accuracy and the low loss comes from embedding. And once you get that set pretty well, then go ahead and switch to the trainable part, the trainable quantum parameters. So all of these are basically a sequence of experiments that I'll be going over. And I wanted to basically go over this. What it looks like is there's an effective number of parallel qubits with these. So whether you have a single qubit that you have 320 of those, which is 320 effective, parallel qubits, or you have 162 qubits all the way up to, say, for instance, like you have 32 parallel 10 qubit circuits. In general, the loss and accuracies are pretty similar. And of course, you don't want to run these huge qubits when you don't have to, but sometimes because of the number of dimensions that you're working on, sometimes you have to run larger quantum circuits. And of course, this is all in quantum simulators, taking advantage of quantum mechanics on GPUs or high RAM CPUs. So an example of this is the nomenclature, and then for the final write-up, I'll include some of the the actual visual circuits of what these look like, although there's a fair number of these. A 4Q8L means that it's a 4 qubit circuit, and there's 8 of those in parallel. And the term is 32 effective parallel qubits. Now you can get to 32 in different ways. So you can have 8 qubits, and running 4 of those in parallel. But that's basically the nomenclature that's used in the demonstration. So starting off is you always have to benchmark, right? You could be wasting a lot of time if you're not running the correct devices, and most of these are economical, even if you're running like an A100, unless you have like 5 instances open and that's just your thing. And you're draining your Colab account. But in general, what's available now is this default qubit, which is the most widely accessible of PennyLane simulators. and then you're running on a high RAM CPU. Now make sure to choose the high RAM, not only for the RAM, which is 51 gigs, but it's about twice as fast in a lot of the runs. So as far as efficiency goes, highest efficiency is going to come from the one that runs the shortest, and then it costs the least. So you see some of these efficiencies getting up into the hundreds or 2000s, and it's just 1 over time times cost was used for that. So this first one is basically batch size. So again, these vary a little bit from Keras to Torch. And, basically this is a good running algorithm, way better than the author's algorithm. And it's not their fault. It's just, I've spent a lot of time on this. So 4 rotational embedding gates for this. So on this one, it actually favored the, 6 and 8 qubits at really low batch size. And like I said, like the whole trend with this is getting higher and higher effective parallel qubits at lower of the qubit size instead of, so say for instance, using 4 qubits or 2 qubits, and sometimes you can actually use 1. Now, what it shows is basically this, is that you'll see this increase in runtime for 8 qubit versus 6 versus 4. And these are combined runtimes in the model. There's a sequential model plus a module, or like the neural network looking one that's associated with this. So what you see here is basically, it's a function of learning rate. Now, the one for Torch varied a little bit, but basically the model of this 0.2 learning rate, and this is very, any single circuit, like a 4 qubit, 1 layer, which is just a 4 qubit circuit with this 4YE algorithm, tended not to work well. In addition, the Keras one, it did not. So say if this was run inside of their neural network module, it'd probably be better, this green and yellow. But regardless, the biggest thing with this is it was actually about 0.37 for this, it was the lowest loss. So I used 0.37 across many experiments, and then I actually reran the learning rate experiments on PyTorch at a later time. I'll show you. Now, in all these things, you have to consider data set complexity. And I would say a lot of these, so the 0.10 at the bottom here, 0.11, they're pretty equivalent. But once the data starts, overlapping, with each other at this 0.2, we used a lot. It not only was, it's expected that you'll take a hit with the accuracy and then the loss too. And this showed actually, somewhat linear increase in loss, which is good to see. So if you run a variety of data sets, like 10 of these, and they're not running predictably, something's wrong, right? So these are similar, but they're added complexity. And anyways, it's good to run this once just to see and make sure things were running right. Because you always want to double and triple check your results with these things. Now, this next one, again, is a function of, these single circuits are a little bit off, I think, for the Keras, because the sequential model, I don't think, is running quite correctly. But what this does show is basically increasing layers, trending to lose loss, and it just depends. But you see a 4 qubit 6L in this specific one did a lot better than the 4 qubit 2L, which these are equivalents running, inside the neural network architecture and Keras. But this is always the case, right? Like there's always usually a lot of different combination of parallel circuits that run better than a single quantum circuit in these models. Now, these next couple are basically training and validation loss versus epoch. And what we look for is basically convergence. So this particular algorithm is a 4YE. Now, it's 4 rotational Y gates. And, so it's a layer. So 4 layers. And actually a 7 RYE was found to be even better. Now, you want the training loss and the testing loss or validation loss to come to a similar value, right? And a lot of times the training will start higher in loss. So the lower loss is preferred. And all of these converge pretty well. So that's the moral of this story with this slide. Now, an experiment, and this kind of gives you an overview of what these look like. So say if the author's circuit was this angle embedding an RX gate, or I call it RXEs, and then you have basic entangle layers, which is this variational training part. But again, if the embedding part is not good enough, like you need more gates just to get a good embedding. The machine learning part, meaning the quantum trainable layers part, isn't going to get much better, because that was the case with these. They're all about, starts out at 86%. And, through these modifications, instead of going parallel, going in series, it actually decreased the efficiency or the accuracy of the models that you can see here. Okay, so this is getting into the core of the torch stuff. Are there any questions at this point? I saw a number of people coming on. And then, so feel free to unmute, and then you can also come on as well if you have any questions, or you could hold them to the end too. And then, so basically, I needed to know, a single circuit run in a torch.nn module, how does it compare to the one in the model that said sequential, which was run separate than the layers, So a single circuit in the torch.nn module, this neural network kind of framework, actually has a little bit better performance than running it in sequential through torch. Now in Keras, as I mentioned before, I don't think it ran well at all. So that was the trend with a lot of those. But the ones in Keras with neural networks, meaning 2 or more layers, they ran more predictably. So that's what was shown here, is basically, there's other studies too where I'll have a single layer, meaning a single circuit, go to 2 layers, 3, 4, 5, and then you'll see that there's always a performance boost. Sometimes not immediately at like 2 layers, but usually within this 4 to 5 layers, and then it starts to really take off as far as performance goes. Now this next one is basically with an 8 qubit, and it effectively, like, I was just like, oh, 8 has to be better than 4, or maybe I could run 12, so I did some 10s, and I did some some 16s too. But at the end of the day, it has to do with, this is classification, and we're talking about embeddings, and it's less about entanglement, and it's more about how data sets are mapped over the surface of this block sphere that we're representing inside of the quantum simulator. So you see in this one that the 8, which is 8 effective parallel qubits, in this case is, you see it's wider, so it's better performance, and it's more effective qubit. So there's nothing necessarily special. So, say for instance, a 4x2, 4 qubits, 2 layers, may produce something very similar to this. And I didn't find out all this until a little bit later. And this next one is basically kind of the big introduction to running more and more layers. So as you can see, the loss continues to go down. Now, this 0.1 data set, I couldn't get for 2 qubits and 64 layers. I couldn't get it to 100%. So I was able to get on this specific one, doubling the data, and actually that made an easier data set. I was able to get 100%, which also, was a better loss and accuracy from before. And this 0.1, I got 100% at later times a lot. After kind of figuring things out a little bit more. So this particular one is basically, there's 2 sequentials on the left. So it's showing that, yes, there's, when you compare a single circuit to any other parallel circuit, it should be running in the same torch.nn module. Okay, so there is a difference if you run in sequential. So if you open up this model, you typically run a single circuit in sequential, okay? And there's a way, and you can see in my code, basically there's a way to run that single circuit and then 2 layers, and then everything on up to, I got up to like 320 layers or 320 parallel algorithms. So in this case, you'll see the standard trend is basically at the second layer and the third layer, for the 4 qubit, not enough effective parallel qubits until the 4th, and then the loss goes down and down and down, pretty much following that trend until 8 layers. Now, it was the same thing for 8 qubit, 8 layers, and then you'll see this, peak here this is a single circuit of 8 qubits, and then the black line is the loss that goes down. And actually, the red one is for training and the black one is for validation, and they converge quite well. And some of these, so say for instance, a 7 RYE that's set up correctly with batch size and learning rate, that tends to, converge almost to identical values. So you're kind of putting all these things together and just thinking like, you're testing it with all these different data sets, and, basically narrowing down to truly understand the performance of this. And then this particular one is very similar. So 4-qubit single layer, i.e. a single circuit, compared to 8 layers or 8 parallel algorithms of 4 qubits is, better. So the loss on this one, and this one, the scale's kind of up because of some of these other, initial training losses up here. But the yellow and the green converge better than the red and the black is what's going on there. Now on this particular one with the 8 qubits, so this is 64, 8 times 8, effective parallel qubits on this one, that these are even closer. And what was included with this one on the next slide is this is a 3RYE, which is a decent embedding algorithm, and just increasing it to 7, able to get this 100% on this 0.1 noise data set. It's trickier because there's one of these orange dots is kind of out, a little bit statistically farther than maybe it should be. And, so that's what it took to get 100%, is run these studies. And then, you can't run as many RY embedded gates as you want, or those typically work the best, but there's limits, so if it's, I think it's 8 was the best in some case. So that's all what we're getting for here. And then, so this next one is basically, it's a single circuit 4-qubit, and this is, 32 effective, parallel qubits on the yellow and the green. So you'll see the yellow and the green outperforming, and these are both done on, these should both be done on module that instead of the sequential. So they're more apples to apples. So I think the main point here in this specific slide is, yes, increasing the number of rotational gates helps to a certain point. And I could probably take this one out a little bit more. And you can actually combine some embeddings, and IQP is thought to be this amazingly awesome, algorithm on paper, but it's typically harder to run. But I basically tried 2 embeddings that didn't work in that case. But as this green goes to 100% at 7 RYE embedding gates here, that was the main thing, is just adding more and more of these, keep decreasing the loss and keep increasing, the green, which is the 100% up here, which it kind of disappears up into the 1. Now, this next one is basically, so this is, okay, so, those that are not patient with embeddings and classifications, and you just want to run as many trainable quantum algorithm parameters as possible, that's not usually the best bet. So this had a decent, so 4YE, a decent embedding. And the BEL is Penny Lane's basic entangler layers, and it has a mixture of CNOT gates, or 2-qubit gates, and then rotational gates. And the rotational gates can change over the course of the epochs, so they're optimized just like, a machine learning algorithm would be optimized. So you see in this case that, especially for this, single circuit didn't help that much. And then going up to 8 layers, again, so some of these, you could call it gestation of 2, 3, and 4, layers, that sometimes those aren't the best, meaning parallel, quantum algorithms. Getting up to 8, that's where you start to see the trends, is this yellow line. This specific one, the trainable rotational gates are probably more effective than the CNOT gates. And I actually removed some of the these in primitives in a different study I'll show you here too. Okay, so this is a huge study. Now the scale is not exact. So you go 4, 8, 12, 16, 4. But in effect, so if you have 16 qubit single circuit, which is 16Q1L, that had very similar loss to a 4x4, right? So 4 qubits circuits, and then there's 4 of those in parallel. And this trend increased all the way up to 80. So the loss kept going down and down, as you see this red kind of go into the baseline there. And then it stopped at about 100. So on this next slide that I'll show you, keep in mind it goes 8, 10, 20, 40, so it's not linear. Like it'll, look a little bit different, but the trend is still there. So anyways, yeah, you always want to increase, especially if it's smaller circuits, and you can run smaller circuits if your dimensions are lower, then, run 2-qubit, 4-qubit. Many of these in literature should be run again if they're only, using 4 qubits and the results are about the same or a little bit more. That should, bring greater performance according to the study. Now, this is actually the same as the previous slide. So this is a 2 of 2. And you can see that the 16-qubit single circuit, 16Q1L, the RAM goes way up, right? So this is, I have 51 gigs to use, and it's going up to 32, a little bit above that. And you can see the runtime a little bit. Now, with this other one, and it looks like it's actually more linear, that the RAM and runtime go up, it looks like at a constant rate according to some other slides, but based on the scale, it just looks a little bit different. But nonetheless, a larger runtime is a lot easier to deal with an exponentially increasing number of qubits. So 16 qubits. So run a 4x4, some other combination to get to the 16 in many cases. Now, this next one is basically stepping it up. So this is basically, you'll see on the left, it's 7 RYEs, which is a really good embedding algorithm. And it's compared to the middle one. So the middle one, which is a more traditional, so Hadamard plus 4 rotational embedding gates. That one tended to give lower loss, but the good thing about the 7 one is that on training and on validation loss curves, it tended to give very good convergence between the two. And even if it was a little bit higher than this, H4RYE gate, is that basically, it's preferred because by the time you put on all these trainable, quantum parameters, a model that's training better is preferred over, something that has lower loss, but there's a bigger gap between the train and the validation curve with those. Now, on the right is basically, trying to get, these quantum parameters. Now, the issue, like I said, is like, I don't think it's been fully proved in any case of adding entangling layers, significantly increasing the performance of in classifications with quantum circuits. But nonetheless, it does have some trainable parameters, and actually adding it to the H4RYE embedding actually improved the loss, meaning it decreased and got 100% in that case. So there's good things going on with this. Penny Lays calls it's a template, or in literature it'd be called an ansatz. There's good things going on with it, but there's also other templates that allow you to customize more, so you don't have to run these other types of gates that might not be as beneficial as some of the rotational gates. And this next one is basically, so this is a 0.2 noise. So if you look in this lower right-hand corner, you'll see a lot of these orange dots intermeeting with the blue. So these ones are a little bit more interesting. If you had an awesome, so I've done brain images before, and I had like a 10 class that worked really well. And it was representative of, say, like, there was enough images in each of those directories to represent that glioma or meningioma, those types of things. So it's not always like these are smaller, and this is what allowed me to do a ton of these studies and get the relative performances, before moving on to, higher dimensions, bigger data sets too. But you can see basically here, this is an algorithm study with a harder data set. And, just the trend with this is basically, especially coming from a single rotational gate, the best one was actually 4. So run 4 rotational gates with this. And then compared to the HRYEs, which is Hadamard gate, and then, additional rotational gates with this, it's, you can see the curve is smoother here, but what is not shown is basically, the convergence. So say, for instance, like the 4YE train and validation loss curves is likely a lot more consistent. And it was interesting because these Hadamards, actually run a little bit faster, even if it's additional gate, so you have Hadamard plus X number of gates, they actually run faster, and technically should have more cost or be slower. And this is what's shown there is if you look at the peak here, so 7 RYE compared to H7 RYE, and this is pretty consistent across all these. So you're looking at 7 gates compared to 8, and then the 8 gates ran faster. So whatever, these quantum mechanics in the computer, it's just, it just runs faster. And you'll see, so basically, runtime, more than the RAM, and RAM's not an issue, that much of an issue in this specific case. Okay, so this next one is basically, this is scaling up. So this is 160 effective, parallel qubits. So we're looking at train and validation loss. Now, this is the curve that I've been alluding to, and basically that you want them to go to 0. So going from left to right, the first 3 are standard embeddings. So this is just to get classical data and the quantum states. And then the next, several are basically different iterations of that. And, some of these, this 4YE with, basic entangling layers, with the C0 gates, not as good. But the one that worked the best was, in specific is this one. So on the 0.1 noise data set, it's 7 RYEs plus basic entangling layers. And actually, I'm sorry, it's this one. It's 7 RYEs. And it's a specific circuit that you can take out all of the C0s. I had to run this because I couldn't find the gates. I just needed a single trainable layers of rotational gates, which is very easy to do. But for this model, it was... I tried so many ways, and I've been on Xanadu discussion forum. And anyways, it actually includes a perfect RX, RY, RZ partition between the 3 of those. And then, so that's what gave it, in this specific case, this, so this would be train loss of 0003, and then a validation loss of 0002 for the 100% accuracy in this specific case right here. And as you can see, the 0.1 noise data set, I think, and as far as like the way this model's set up and not being able to train extensively, there's only like 200 images on this, is that it did reflect things, say for instance, if an algorithm's supposed to work better here, and typically did, but the performance was not quite as consistent. And I was able to get some improvements, I think around this, or maybe a little bit below this 0.02. But basically everything from here to the right are, from the harder data set. Now, this next curve is basically looking at, so this is the big study. So this should be, this is important. So you have to find out what batch size tends to work best for all of these. So for a given 8 layers, meaning 8, parallel quantum algorithms, is for 2 qubits, it's somewhere between 7 and, going up to 12 in this specific case. And it's actually the 10. So for 2 qubit, 8 layers, batch size of 10 is the best for that. And then going on to the 4 qubits, it's actually somewhere in here. I'll put up the tables later, but you can see, batch size of 3. So the 2 qubit also has the spike, but it's not within the range that it had its best batch. That's why it's not shown. Okay, so 4 qubit you'll see here. And then the 6 qubit actually did quite well with accuracy. So these 100% right there. And then, you can see that the losses were relatively low. And then you could see, early on in the batch, so a batch size is basically amount of data that's sent through at a time with machine learning. And this is the same thing for quantum inspired machine learning. So, you see it's really not favorable at this lower batches, but in this case, I think it was 4 or 5, something like that the loss was best. So in all these things, you're not going to get into RAM problems Again, runtime is easier to fix, just switch to better hardware, but the RAM is a huge issue, as you get up. And you can see that the trend with this is basically, get up to 4 qubits, RAM increase, or I'm sorry, runtime has this spike here, and then another runtime spike, and then another one here. So, maybe not completely linear with runtime and RAM at the same point, but you can see with the purple, the purple jumps more from 4 to 6, and then from 6 to 8 has the biggest jump for RAM. So when you're running, anything quantum inspired, with these, new classes of algorithms, you have to be careful of, certain circuits, especially 10, 12, but especially like 16s and those things. And there's actually ways, it looks like, if you have many dimensions, to separate dimensions, like this set of 4-qubit algorithms gets this dimension in a bigger dimension set, and then this one. So kind of like an ensemble learning, those types of things. But anyways, it's just, you have to be aware. And again, with these 8 layers, 8 qubits, 3 a little bit above gigs of RAM is not very much. And then, so this next one is basically showing, these are layers. Okay, so the batch size has been set. So the best batch size for 2 qubits was 10, for 4 qubits was 6, for 6 qubits was 4, and for 8 qubits, it was 5. So then what this shows is basically this gestation period of, you have from a single layer, which is a single circuit, in all of these is not good, right? So it always helps to start this journey. And again, for 2 qubit, it took until, 5 layers, you have to get up to these, 10 effective qubits for parallel circuits. And then you start to see this much lower loss. And this is where, it's at. And the accuracy in these cases that reflects that. And then for the 4 qubits, you'll start to see it pushed up. So instead of, actually, the accuracy improves at the same number of layers. So it took 5 parallel quantum circuits in order to get this specific low loss. It actually improved until 8. So for a lot of these, the max is typically the more layers, the better. So on some of these, you see the purple go down and down. And then you see for the 6 qubits, the 8 being good. And then these are up actually 100% as it starts to diminish up there with accuracies. And likewise with the 8 qubit, and it just had a little bit of spike here. So occasionally these things happen. I with the parallel quantum algorithms, they're a lot more predictable than, single circuits. And you're just going to have these things where you'll just hit it right on the dot, and it's like extremely low loss, like 0, and it converges to 0. It doesn't show any sign of overfitting. And then this 5 one was a little bit more mysterious, but I'm sorry, 4 layer, and then going back down at five layers there too. Okay, so how does this look with runtime and RAM? And it's a similar type of thing, but as you can see that the RAM, is more steady. And then the runtime, especially, getting up to this 8 layers with the 6 qubits, and then 8 layers with the 8 qubits there, you start to get those peaks. But again, we're not talking much time. So this would be, 3.5 minutes compared to 4 minutes. This is on a CPU, right? So, you kind of put all these things together, and it seems like there's huge benefit, especially in running some of these smaller, qubit circuits, and then split up different dimensions, as they do, traditionally. And this next one is basically batch size or learning rate. So this is a new study here, and it's basically, I wanted to find something, this is probably the most unique out of all of this. I wanted to find something that I could show that if I found the best batch size, or for this given 10 qubit 2 layer, or if I found the best learning rate, the best algorithm, the best number of layers, and there's one other one, there's 5 total, what has the biggest impact on decreasing loss, right? So, the batch size was found to be at this 3, for this, it's 20 effective, parallel qubits here. And then, it basically stops here. And then the learning rates, this is a broad range. Learning rate is pretty much constant over the course of the run, which is good to see. It was 0.52. So From Keras, it was looking more like 0.37. So there's a little bit different. But anyways, you know, the 0.52 in PyTorch with additional experiments was just, you know, really, really good. So this next one shows the, you know, runtime versus RAM. And so you'll see that the RAM only, and for these, you would expect the RAM to increase a little bit for batch size. And you'll see a more dramatic thing if you get up to, you know, hundreds of layers, those types of things, but this is just 2 layers. And then for the learning rate, you would expect, well, it's about the same. But the biggest thing here is a low batch size, you know, meaning that if there's like 150, 200 images that you want to give all at the same time instead of splitting it up in batches. So, you know, if you have 200 images at a batch size of 5, that's 200 divided by 5, and you're running those smaller chunks of batches through at a time. But basically, you know, the biggest thing that this shows is, you know, if the batch size of 3, which was shown before, is the best, and then it's kind of coming down. So it's basically, you know, it's not the very fastest method of doing it, but, you know, batch size of 7 on the previous slide did not have the best performance. Now, the thing with this one is basically, you know, so these, okay, so it's algorithm, circuit size, or parallel layers. Okay, so the very first ones here, these are all algorithms. So as I showed before, you know, 4 YEs or 7 YEs, and in this case, it's actually 8. 8 was the lowest loss, and that corresponds to this accuracy here, where 9 and 10, you know, too many gates to the algorithm. Okay, so that's what that peak is. And then this next set here is basically, and this is the whole crux of the study. So I chose 10 qubit 2 layers because a 10 qubit 4 layers is too much RAM for 16 qubits. So that was my limiting factor. So anyways, between a 10 qubit circuit, 11, 12, 13, 14, 15, 16, it was actually the 15 that ran with the lowest loss. And the crux of this presentation and everything kind of paying off is increasing the numbers of layers. Is with a single circuit, the loss is higher, and you can see it improves with 2. And this is the basis, you know, 10 qubit 2 layers. And then as layers are increased, it's the best overall loss, you know, with these, with increasing the number of parallel algorithms. So how this stacks up, and this is a zoom of that previous slide, is this loss corresponds to 0.0069, right? So it's not the best results I had, but it's inside this study. And it's better than, you know, this having 8 rotational gates. And it's only changing one thing at a time. So it's still a 10 qubit 2 layer study, but in one of them, it's changing the algorithm. And another one, it's increasing qubits. And then in this last one, it's increasing layers. So again, the basis shows up here on this 2 layers, and then it's the same right here on this 2 layers. And then I don't think actually it's shown right here. So what this equates to is if all of these losses combines, and by the way, here's the default setting, batch size 5, learning rate 0.2, algorithm, and then the 2 qubit 2 layers, is that the parallel layers out of all of these other ones, these 4 other ones, circuit size, algorithm, learning rate, batch size, optimizing all those, is the best way to decrease loss and increase performance in the model. So I didn't know if that would be the case, because obviously it seemed like, you know, going from 20 layers to 40, you know, in running these, it kept decreasing loss. But that was basically not planned. But, you know, the experiment was set up for any of these to, you know, improve performance the most. And it wasn't just, you know, the number of layers. And so this is the issue. So you saw this peak before. So this is the 16 qubit. Now it's 2 layers. And then you saw with 1 layer, it was like 32 gigabytes of RAM. And now this is up to like 50, right? So you see this, and basically it's not as much, and you'll see this RAM and runtime increasing, adding on gates to the algorithm. And then right here, adding on additional qubits is, what really does in the RAM, right? It's very exponential in RAM, right? So it'll get to the point, you can't even run whatever circuit, just because you don't, and nobody else has that amount of RAM. So, what this shows is basically this is the linear, going up from 1, 2, 3, 4, 5, 6, 7, 8, where RAM and runtime are more linear together, right? So this is the first time I've been able to show that on a more fundamental level. And remember, this 8 layers from before had the lowest loss and the best performance. And then, so this is, okay, so what this is here is basically I took those settings that I learned before. So the ideal batch rate, ideal learning rate, ideal number of layers, and I applied it. So the ideal number of layers was 8, right? So I used 8 layers. I used, the best algorithm, which I think was the 8 RYE. I combined it all. And basically it helped, right? So these are lower than, the slides before. And you could see, say for instance, it goes 1 through 6, and you want convergence and you want lowest loss. So on these specific ones, they're similar, for 10 qubit, 8 algorithms parallel, but they're not the same. Okay. So when the number of algorithms is increased from 8 to 60, then over the course of the run, yes, it does start off, with training being much higher, but then epoch 2, meaning the second iteration in machine learning, they're closer, and at epoch 3. So and actually between epochs 3 and 6, the train loss is equal to the validation loss. And this is a good sign to see. And the validation accuracy is actually 100.0%. So between 3 and 6 here, it's perfectly trained. And again, this isn't the hardest data set in the world, but it's something that, initially I could only get 99.5, and then I got 100%. And then, to have this perfect train and validation loss convergence there, it's a good sign. Okay, so this one in specific, so this is basically showing effective qubits, so effective parallel qubits. So this is basically a single circuit with 320 parallel algorithms, a 2-qubit circuit with 160, a 4-qubit circuit with 80, an 8-qubit with 40, or a 10-qubit with 32. Now, the only one that was kind of out of line here as far as loss and accuracy was the 8. And as I said before, this just happens. It's not, it's a very good thing to use parallel quantum algorithms, but occasionally, you're going to have a trend. And you take this as the first equation, 1 times 32, 2 times 160. They all equal to this, 320 effective parallel qubits. Now, I wanted to really show that machine learning helps, okay? So in all of these previous ones, 1, 2, 3, 4, 5, it's just an embedding, right? And you can go pretty far with performance and embedding, and other researchers from Xana too have said similar types of things too. And I put on the best trainable algorithm, and this specific one does not have CNOT gates. It's just actually a mixture of RX, RY, RZs, and they're trainable. So yes, you can run just embeddings in machine learning, and things get optimized over time beyond just the parameters of the gates. But in these ones in specific, you can see that they're actually not supposed to run much better than one or the other. First qubit, second qubit, 4, 8, 10. They're all equal to it, and effectively the same number of effective parallel qubits on that. So on this next one is basically, and these don't, they don't vary too much, but basically it's expected to use more RAM, right? So runtime actually corresponds better between each set of experiments. So these compared to these, the second set, as opposed to, this increase in RAM. So, and this is anticipated. So if you have a smaller quantum algorithm At 10 qubits, it's represented by this this yellow one here. So you'll see the peak right there. And then like here, so 10 qubits at the bigger variational quantum circuit, like a full circuit, you see this yellow one up here. So the trick is to do your task with the lowest number of qubits. And, based on some, research that I've been doing, it looks like you can run smaller quantum algorithms and, say have 4 do this dimension and do the, do 4 for this one. And then like ensemble the whole classification task, because they are state vector circuits and they run just like state vectors. It's just that information is spread over that number of parallel algorithms. And so basically the conclusion with this is that, starting off from the beginning is, we have to have compatibility with NVIDIA or AMD, with GPUs, getting outside of default.qubit, more into lightning.cocos or lightning.gpu. And then the second point here is basically, I've kind of nailed down the single circuit issues with Keras. It looks like it's the sequential, but there was other issues related with Keras, like installing the right version of TensorFlow in order to it to behave properly. And then, okay, so this other one is basically the torch.nn.module single circuit performance was a little bit was always lower. Well, I'm sorry. Some of them, like say between 2, 3, and 4, especially for lower qubits, because the effective number's not up, it did take a little bit initially to kick in to get better than a single circuit. So that's the thing. You have to test this very thoroughly. And then, these Keras initial studies helped and kind of bringing it all together with PyTorch. And then if your multiplier is not that high, you have to be careful if you're running a 1 qubit, 2 qubit, and you're only running like a couple layers, you're not going to kick in yet as far as like the benefits of truly running, parallel algorithms efficiently. And, the embedding has to be correct. So, your embedding gates, and it's typically rotational gates work the best. And I've heard this from multiple places. And some outclass the others. So even though a Hadamard and then, rotational gates might actually run faster with less RAM, it tended not to have the better convergence of just running single, rotational Y gates. And I guess the easiest study to understand is if you know quantum circuits and if you've tried to run like, 16 to 20 and, some get up to 30, is your RAM just shoots to the sky. And the trick with all of this, like I said, is to run, because these are decreasing, loss, increasing accuracy at less RAM and faster times than single circuits. So a good example is that 4 qubit 4 layer versus the 16. And let's see. And the runtimes for, a single qubit, 320 of those in parallel versus 8 qubits were similar, but it's the RAM that was markedly different. And, as I mentioned before, the 0.2 noise data set, and that was actually the hardest one that I used. You can see the data is just like, there's one dot that's almost kind of like overlapping one. And actually, a lot of them do that. It was expected that the performance would be lower, but it was less diagnostic. It is more stochastic as you watch, the machine learning do its action. And obviously the potential application for this is, I've mentioned this, I think twice, is basically you're going to have, if you have bigger data, more dimensions, and it sounds like this is already done, traditionally, is now have, blocked off sets of parallel circuits. This does this dimension, this does that. Because again, they are regulated by, state vector algorithms because they are them. And it's not necessarily opening up more dimensions, because it would, even if the performance is there, you would have to run, multiple sets of parallel algorithms, it looks like. And the big study, is basically this, is modifying all these other parameters to their best, with the learning rate and batch size, and the biggest impact was the number of trainable layers. And it would actually continue to improve. So it didn't actually max out with resources, from RAM, from qubits. That was the big one. And, you can only find the best, learning rate or batch size, once. That's the max. And what I anticipate is basically the industry has done a fair amount on this quantometric learning, from MIT, Xanadu researchers, and they always had the issue with overfitting with it. And there was a demo up there, and it's super important, right? Like the embedding has to be right. And I found in 2 other studies on my own that yes, you can improve the whole thing with other trainable quantum parameters that change over the course of the run. But that needs to, in my opinion, need to be revisited, right? There was too much behind that just to say now we have overfitting, but you didn't run them in parallel. And there's a slew of these papers out there that all run 4-qubit single circuits, and the performance is pretty similar, between the traditional approach and running 4-qubit algorithms. But in my experiment, and I think probably in theirs too, is it's when you're running a single circuit, it's just very specific as far as like, you're basically getting great performance here, then you adjust it a little bit. And you see with the parallel circuits is over the course of all these, changes in learning rate, didn't change that much for that data set. And then, it's a lot more robust system than through all these studies, seeing these single circuits just not perform very well. Awesome. I saw a number of people hop on here. Are there any questions at this point? Any of the slides to take a look at? It's good to see a lot of familiar faces here. And then, so feel free, so you can unmute or unmic yourself. And, no matter where you are with your journey, this is, in my opinion, a good place to start. I took this quantum transfer learning demo, from basically like a couple hundred images of ants and bees to like 4,400 images with brain tumor images. And then the performance was a little bit better than the classical. But if I can get the parallel algorithms, meshed with that demo, then, based on this and the different data sets, that looks like that would help the whole thing. Like it has to be significant, right? People aren't going to want to switch to quantum algorithm if it's not significant. And then any questions? So there was a number of things that were covered, any just basic questions about machine learning or quantum machine learning?
Hey, Kevin.
Yeah, go ahead, Ron.
So, I've seen some of your presentations on this. I'm wondering if you could give a more in-depth definition of what you're talking about when you're talking about parallel circuits within the context of what I assume is like Penny Lane and their simulators. What is the physical attributes of a parallel circuit?
Yeah, it's basically using, so it's split and concat from torch.nn. So the QML.QNN.torch layer, packages up the quantum algorithm, that uses, all of this information. And then it's now inside of a regular torch.nn.module. So, the way it works is basically, if you have, say, for instance, like 4-qubit circuits, they all get the same information at the same time. It's literally like splitting it, but it's sending it to all 4 at the same time. And then you get that added processing benefit, and then it gets concatenated. So over the course of, if you have like, if your batch size is 5 and, your total size.
So those 4-qubit circuits are potentially each running on their own simulator?
No, not, it's basically, that's the way that it was described to me, is basically, it's not, they don't get separate data. They all get the same exact amount of data. So it allows it to be processed, instead of like, say it didn't get processed well the first time, the second time, the third time in a single circuit. Now you're getting more, effective algorithms all at the same time. Right. So I think that shows up
So,
in,
yeah, so you got you got four qubits in each circuit, and you got four copies, and you're giving each copy the exact same setup, the exact same data. So it is the benefit here because each one of those circuits runs on its own simulator at simultaneously.
no, I don't think it runs on its own similar. I think it's like directly related to the, you saw the one slide where it was literally increasing number of layers is just linearly increasing in time and in RAM at the same time, like both
Well,
together.
sure, adding layers, but uh, are those layers considered part of the parallelism then, or?
Well, it's effectively, they're the same algorithms, right? So it's not necessarily going to require, and you can actually, as far as I know, you can run multiple, quantum circuits on a same simulator, and these types of things. You have multiple devs and those types of things, but it's effectively, instead of just one thing doing it at the same time, it's just that same information being split across four of them, and then that information is concatenated, and then it goes in a more efficient processing method, for loss.
So possibly the penny lane simulators have a single simulator has the ability to partition the circuits, so they don't
Yeah, I
have
mean,
to
there's
maintain a state vector
yeah,
for
there's
all 16. They just maintain four state vectors, one for each circuit.
Yeah, and all of this has been established in machine learning. So it's in specific, it's torch.nn.module, and then there's a forward pass after that. But parallel algorithms, like classical algorithms, traditional algorithms, have existed for some time. And there's, you basically, there's, you know, in a specific machine learning notebook, there's many algorithms, and there's classical algorithms, and it doesn't necessarily just take. I think that you could do a lot more with a single simulator than just a single quantum circuit. But it's basically in that core, torch.nn.module, that's they're effectively, it's quantum mechanics, which is programmed into the quantum algorithms, but it gets converted into this traditional data set or module that's existed for some time.
Okay, so but basically the benefit of using a parallel model is it keeps your RAM demands down. Is that
Yeah, so
fair?
increasing qubits, on a circuit is gonna kill RAM. But that allows you to get these higher dimensions, right? So, if you run super low, number of qubits like one or two, then if you have your data set has so many other dimensions, then you have to come up with a different solution using them in like blocks of parallel algorithms.
Okay, all right.
Awesome. So, okay, anybody else that we haven't heard from? So yeah, there's machine learning, quantum inspired machine learning, which are very similar. You're basically just have these new classes of algorithms that have quantum mechanics, and they get converted back, processing this data into something like the torch.nn sequential or module. If you're doing parallel, it's going to be module. But yeah, just very similar. Are there any questions regarding anything like that? And I would highly recommend anybody becoming an expert in machine learning. Um, it's a steep learning curve, but you just you have to know everything about machine learning. Anybody else kind of want to? So this is this is actually the last discussion of the year. So happy New Year, everybody. What's that, Sunday or Monday? Monday. And anybody else want to share a story, a quantum story, you know, algorithms, applications that they've used with quantum? Things you're looking forward to doing with quantum too.
Well, my most recent venture is is working with D-Wave and attacking cubo problems, quadratic unconstrained binary optimizers to use quantum to optimize various algorithms out there. It's not machine learning, but it's very satisfying to get results from that.
Yeah, it's a broad field for sure. And I'll very likely just be honed in on the QML. It was a journey to get to this point, but I really, and this goes to everybody here, there's that application, there's many other ones too. Now, I think the biggest driver is practical and readily available. And it basically, you could use it just in substitute of machine learning, which is a huge field to begin with. So effectively, you're using parts that already work, right? And it's just this new understanding of quantum mechanics and algorithms that you're tying it into. So yeah, for anybody in your journey, definitely map it out, the financials, like what it's expected to be, like what exactly will this problem solve in a year from now, when the hardware gets fixed, or if this algorithm works better, and say you implement parallel algorithms into some other demos you're working on. I would really take the time and do that, right? Because is it practical? Is it efficient? Does it work? I think it's the main thing, right? Because you're get hooked on a specific technology, but say for instance, it's still many, many years out, especially for like QML workflows, but yeah, if you get paid for whatever and you're happy doing it, in quantum, go ahead and do it. But I really think there's a huge breakthrough just sitting there for QML, right? GPUs, quantum algorithms, machine learning is the best way to describe it to people that And there's, like I said, it already works. It's just the understanding needs to get better applications, better, techniques to process, instead of single circuits, do it this way. Those types of things. Awesome. Any other last comments or questions? So anything related could be healthcare too. Healthcare data is fair game. You can't Kaggle data sets. There's a number of brain tumor image data sets for classifications to use. And start with the quantum transfer learning demo. Now run a GPU, but it's not for the circuit because the neural network takes up more processing than the quantum circuit. So one will run faster than the other one until this whole PyTorch and Keras and Penny Lane and even Qiskit too. Qiskit has PyTorch stuff. It has to get. It's probably just a switch they're waiting to flip, but I don't know. Awesome. Anybody else we haven't heard from? So you could come on, wish a happy holidays. I think for everybody, it's pretty much the happy, the New Year's coming up.
I hope everyone has a safe and happy and joyful New Year.
Yeah.
See everybody next year.
Yeah, and you
take
can
care,
start.
Kevin.
Yeah, appreciate it. Everybody can start using that phrase. See you next year. I appreciate everybody coming on. Thanks everybody for, there's a number of you that keep coming back, all throughout the year, especially later in the year. And this has been discussion 115, Thursday, December 28th, 2023. Basically for these, parallel, very promising parallel quantum algorithms. Have a good rest of the night, everybody, and have a productive rest of the year. Take care. Happy New Year.
Kevin, Happy New Year to you all.
Yep.